Hi everyone, my name is Chao Bin.
I'm Julian Chan.
My name is Niels.
And this is Sofyan. For our ME 157 project, we designed a TV storage system. Around 1950, the first color television was developed. Now, in almost every house, we can find a television. However, the area around the television has always been an area that was hard to keep neat due to the necessary TV cables. Therefore, the objective of this project is to design a TV lift closet with cable management. Other projects that were considered besides the TV storage system were the tricycle with leaning through corners and the flexible laptop mount. By using the decision matrix, we decided the best project for our criteria. We graded each alternative on the following criteria. The project should be related closely to human daily life. The project consists of sufficient amount of mechanical engineering content, which include analytical content, design content, and flexibility within complexity within the boundaries of the ME 157 course. Creativity as well as market potential was also considered. Our decision matrix concluded that the TV storage TV storage system was most suitable for our project. The next step is to identify how we're going to meet the requirements. We use the quality function development method to analyze our project. So we established the following house of quality. We studied our customer, we analyzed our customer requirements, and we derived the importance by comparing the two. Then we studied what's on the market now, did a full text specifications to fulfill the customer requirements, and studied the relationship between specifications and requirements. The target as well as the relationship between specifications were also considered.
The next phase of the design process is the conceptual design phase, in which we establish several concepts to ensure functionality and select the best concept for our product. First, we perform a functional decomposition where customer requirements determine the functions of the product. Then we will start the concept variant generation. In this table, we can see the customer requirements on the right side, and on the left side, we can see the functions, including the flow of material, energy, and information. Many requirements are basic requirements for a storage device in general, such as high stability. However, the TV storage feature is the main feature that distinguishes our product from other products on the market. On top of that, the storage TV is the main requirement of the product, as it contains many technical functions. Therefore, we will focus on the TV storage requirement in the concept variant generation. Before we do that, let's recap the functions mentioned in the functional decomposition of the storage for the TV. Those are: open the cover when the TV elevates, lift the TV, stop the TV when it's fully elevated and descended, and close the cover when the TV is stored. So for the functions above, for the functions that I just mentioned, we came up with several concepts. First, the elevator mechanism. This mechanism is based on the analogy of the conventional human elevator. There's an electric motor that rotates a pulley. This pulley moves the elevator connected to a steel cable. A counterweight is used to balance this mechanism. Second is the gear and rack mechanism. This mechanism is also powered by an electric motor. An electric motor rotates a gear that is connected to a rack. By rotating the gear, the rack would move either up or down. The third concept is the hydraulic elevator mechanism, which uses a hydraulic cylinder that provides the motion for the elevator. The pressure changes in the hydraulic cylinder, which makes the piston move up or down. With the TV connected to a hydraulic system, we can move a TV in and out of the storage system. The fourth concept is the scissor mechanism. The scissor mechanism can either be driven by pneumatics or by an electric motor. These two power sources would move the linkages in the scissor mechanism closer to each other, resulting in an elevating platform. Similarly, on the way down, the linkages are moved apart from each other. The fifth concept is the belt and pinion drive actuator. In this mechanism, an electromotor rotates a gear that is connected to a static belt. The pinion basically rolls over the belt and can make an up and down motion. The last concept that we came up with is the crank and slider mechanism, which uses a motor at the center of the crank for rotational motion. The crank is linked to a rod at the end of the limit of the diameter and on the crank. The rod is connected to a slider that moves vertically, in our case, as the TV needs to move up and down on the vertical axis. So to select the best concept, we evaluate each concept by using Puck's method. In other words, we use a decision matrix. In the decision matrix, we grade concepts on each criterion relative to the conventional elevator. The result of the Puck's methods are shown in the decision matrix. For the TV storage system, we will go further with the gear and rack lift design, as it received the highest score in the decision matrix. Besides the benefits shown in the decision matrix, this design is also highly applicable to the course material of ME157 mechanical system design. We will further elaborate on the rack and gear lift in the next design phase, the product development.
Okay, I want to talk a little bit about the 3D CAD model we have that is drawn from SolidWorks. So the overall dimension of the cabinet is 60 inches in length, 20 inches in width, and 45 inches in height. And the material for the cabinet is wood. To kind of re-emphasize again the requirements we have for the cabinet, we want it to be minimum effort to install for the customers, and it also includes cable management and high stability. And most importantly, we want to have a enough storage for the TV and different accessories that comes along with it. To keep it simple, we designed the cabinet with a rack and pinion mechanism, and it would be powered by an AC motor. The AC motor would be compatible with the outlets we have usually in our room, so that is convenient. And the motor is mounted on the top of the cabinet, so the pinion will able to run from the top of the rack all the way to the bottom. In our case, the pinion actually stays in place while the rack goes up and down with the TV. And to have high stability, the TV lifter system we have is attached to two rails that is also attached to the protruding section of the back wall of the cabinet. We want to keep high stability. We also design our system with a factor of safety of 2 to avoid any disastrous failure or just in general prevent the TV from tipping over because of an earthquake or any sorts of vibration. To have enough room to store the TV and the accessories, we use a 60-inch TV as our guide for design, and it's perfectly fine to use in TV any size less than that. And instead of having one large opening for the cables to go through on the bottom of the cabinet, we design the cabinet with holes of 1 inch in diameter, so different cables can go through the different holes to avoid them from tangling up and becoming a mess. So here's a little work in action for the whole mechanism. Once the mechanism is turned on, the TV rises up, pushing over the top cover, and it should be fully rise to the position within 30 seconds, and vice versa when the TV is going down.
I will be talking about the stress analysis done for our project. The stress analysis in our design will focus on the stress on gears, as it is the most vulnerable part in our design. Two aspects are important when considering a stress analysis on a gear. The first being tooth breakage that could happen with bending stress, and the second is surface pitting that happens from excessive contact stress. In both cases, it is most important to analyze tooth flow that is delivered from the torque. We will be using bending stress method in our analysis. The rack and pinion uses a 20-tooth, 20-degree pitch gear and a matching 20-degree pitch rack. Both rack and gear are made of 1020 carbon steel with yield stress of 42 ksi and ultimate tensile stress of 57 ksi. The calculated max bending stress is 16,000 psi. which yielded a safety factor of 2.21. The gear-to-gear set uses a 12-tube 20-degree pitch gear mated to a 60-tube 20-degree pitch gear, which gives a speed reduction of 5-to-1 and increases the motor torque by 5 times. The same 1020 carbon steel is used for these two gears. The calculation yielded a safety factor of 1.91 for the smaller gear. The last component analyzed is the shaft. The gear shaft holds the pinion gear and the larger 60-tube gear. The shafts mainly experience fully reversed bending stress from the torque on the pinion gear and the 60-tube gear. The shaft was analyzed using modified Goodman criterion and yielded a fatigue safety factor of 3.1. That concludes the stress analysis part of our project.